Hi everyone, my name is Steve. Welcome to my learning note. In this video, I will share what I learned about time, windowing, and watermark concept in Flink. To discuss this topic, I will use this problem statement of a real-time ride-sharing application that tracks and analyze trips to provide insights into peak demand hours. I will go back to this at the end of the slide and try to apply what we will learn together in this video. So let's begin with notions of time. Flink provides different types of time, but for this learning I only care about these two types. First is event time, this one. Event time is the time at which events occur on its producing device. The timestamp of the event is usually embedded inside the event itself. And the second type of time is window processing time, or processing time. Is the time at which events are observed in the systems. It is also known as system clock time. Processing time refers to the machine's system time executing the respective operations. And the third type that I won't be discussing is ingestion time. It should be right here, which is a hybrid between event time and processing time. I have an example graphic in the slide that represents the relations between events and processing time. The x-axis represents event time completeness in the systems. The y-axis represents the progress of processing time. In an ideal world, event time and processing time would always be equal, with events being proceed immediately as they occur. But in reality, the system lags a bit in the beginning of processing time, veers close towards the ideal line over here in the middle, and then lags again at the end. The horizontal distance between the ideal line to the red line is the skew between processing time and event time. That skew is the latency introduced by the processing pipeline. Things that can be affect the level of skew, like shared resource limitations, like network congestions, or some causes in the software, like distributed system logic, contentions, and other stuffs. So, what is the important distinctions of time? Event time is deterministic and also immutable. Use event time when time accuracy is crucial. Event time ensures that events are processed according to the time they occurred, not when they are processed. This is critical for accurate and determined results, especially for applications where the timing of events directly influence the outcome. Processing time, it always changes. It is not deterministic and mutable. Use processing time when application is tolerant to timing inaccuracies, and simplicity and performance are more crucial factors than the exact ordering or timing of events. Yeah, so processing times is better in performance, but they are not has higher accuracy. Let's go to windowing. What are the main challenges on infinite stream? For the unbounded stream, the data arrives like this continuously, right? So this is based on timestamps in order. If we need to aggregate the data or do any other analytic computations, it is impossible, right? Because we cannot wait for all the data to arrive before processing it, as we would never finish. Another challenge of stream processing is that the data may arrive out of order, meaning that the events must be aligned with their timestamps. This can happen due to network delays, clock skew, or other reasons. Out of order data can affect the correctness and consistency of our results, mainly if we rely on event time. So the solution to those challenges is called windowing. Windowing is a technique that divides data streams into finite chunks called windows. Based on some criteria, we can apply various operations to the data within each window, like aggregations or transformations. So windowing is useful for the unbounded stream. This is because we can process the data incrementally as it arrives and produce partial or approximate results. Windowing is useful for the out of order event. This is because we can wait for data completeness within the window, so we can ensure the late arriving data can still be processed. Flink support two types of windows. First is non-keyed streams or non-key windows. All elements in the stream will be processed together. The downside of this stream type is that it gives no parallelisms and only one machine in the cluster will be able to execute the jobs. And the second type is keyed window. It groups elements to process in parallel. So for example, I have events with different shape. If we use the key is a shape, Flink will group based on the shape and then we'll execute them in parallel streams. So after we decide the type, next we can choose how we assign the events into the window. Windows in Flink can be time-driven or data-driven. Time-driven, for example, like count over the last 5 minutes, right? Based on the type of time we use, yeah. Or it can be data-driven, for example, every 100 elements, things like that. And Flink provides 4 predefined assigner types, Windows assigner types. Tumbling, sliding, sessions, and global windows. Tumbling windows assigner assigns each element to a window of a specified window size. Tumbling windows have a fixed size and do not overlap. For example, if you define a tumbling window of 5 minutes, the stream will be divided into 5 minutes interval, right? From 0, 0, 0 from 0, 0 to 0, 5, from 0, 5 to 10, and so on and so forth. The next is sliding windows. It's a assigner that assigns each element to a window of a specified window size. Similar with the previous assigners, tumbling, but this one it has also fixed size of window, but it also has the slide size, so it can overlap. For example, we could have window of size 10 minutes, right? The red one, 10 minutes, that slides by 5 minutes. So with this we can get every 5 minutes of window that contains the events that arrive during the last 10 minutes. The next window is session windows. The session windows assigner groups elements by sessions of activity. Session window do not overlap and do not have fixed start and end time. So sessions of the window closes when there is a gap within the activity, within the specified threshold. We can specify the threshold of the session gap. For example, if you define a session window with a gap of 10 minutes, the stream will be divided into windows that contains events that are most 10 minutes apart from each other. The final type of windows is global windows. It's a assigner that assigns all elements with the same key to the same single global window. It's a single window that covers the entire streams. Global window never closes by itself. So if you have a requirement to use a custom window trigger, I'm not discussing about window trigger in this video, but there is a Windows trigger. So if you need a custom Windows trigger, then you can use this Windows assigner. Okay, let's discuss about watermark. What is watermark? Watermark they are the way the system measures progress and completeness relative to the event times of the records being processed in a stream of events. What does it mean? Let's recheck this diagram again. The red line, which is the reality between the event time completeness and processing time, is basically a watermark, right? It captures the progress of event time completeness as processing time progress. How watermark works? Watermark is basically a timestamp that added to the data stream. So this is the watermarks that Flink added to data streams at a certain point. It flows through the operators, right? It flows through the operators and tells each operator that no elements with a timestamp older or equal to the watermark timestamp should arrive. Okay. And in this slide, I will discuss about watermark generator and strategy. The watermark generator tells Flink when Flinks need to generate the watermark. There are two types of generators. First is periodic watermark. It observes stream events and generates watermarks periodically, which is by default every 200 milliseconds. Or punctuated watermark. It observes the system of events and emits a watermark whenever it sees a special element that carries watermarks informations. Watermark strategy tells Flink how Flinks need to generate the timestamps for the watermarks. Flink provides some default strategy, but I want to use as an example in the following slide is the for bounded out of orderness strategy. It is a strategy to tell Flink that the event may be out of order within the certain time constraint. So to make it more clearer, let's see an example of watermarks. Okay, so let's say I have a watermarks using tumbling windows of size 5 minutes, and watermark strategy is for bounded out of orderness set to 2 minutes. Here I have the data streams, right? The blue one is the events. So let's say there is an event coming into the streams at this timestamp 8:28, right? So it's trigger the Windows state, so the state is created, and then because the timestamp is 8:28, it will belongs to this window size that between 8:25 to 8:29 5:59 9999. Basically is 8:30 minus 1 milliseconds. Okay, so it belongs here. The next events arrive, right? It is out of order, but it is within the windows, so it arrives in this window. Yeah, Flink will put this event in this window, and then let's say the Flink generates the timestamp. So how it generates the timestamps? It will see the maximum event time previously observed in the systems, which is 8:28, and then it will use this event time minus the size that we set here for the bounded out of orderness, which is 2 minutes. So that's why the timestamp of these watermarks will be 8:26. Okay, so because the timestamp is 8:26 and it is still less than 8:29, therefore this window state is keep open. Yeah, the data that in this window will not be processed by Flink for now. Let's say there is a new event coming in 8:32, so it triggers a new window state and it will be inserted in this time window, right? 8:30 to 8:34, the next window. And then let's say Flink generates another watermark. In this case, will be the maximum, the highest event time, 8:32 minus 2 minutes, so it will be 8:30, the timestamp of the watermark. And because 8:30 is greater than this window size, therefore this window will be fired and will be processed by Flink. Yeah, and then the state of the window will be removed like that. So therefore, if let's say there is a event with timestamp 8:29, it is considered as a late event because it's supposed to be in the previous window, but the previous window already fired. So this is basically no place for this event. So what happened with the late event? There are 3 strategies that we can choose. First is to reactivate the closed windows to recalculate the results by setting the allowed lateness. So by setting this, the windows will be the state of the window will be preserved by the extra time that we set. So late event can still be captured, right? The second strategy is to collect the late events and process them separately by setting the side output, right? Basically, we set additional output streams, or by default, Flink will discard the late events. So let's go into the summary. This is the problem statement in the very first of the video to analyze the peak demands. So what will be the event time that we use for this scenario if you want to compute analytic reports of write trips. So we can choose event time, yeah, because event time is the actual time when each trip started and ended, and it is crucial for analyzing demand relative to the exact time of the day, independent of when the data arrives at the servers. What about the windowing assigners? We can choose sliding windows. Yeah, we can use sliding windows based on event time, each spanning 1 hour and advancing every 15 minutes, so we can see report every hour when the data is updated every 15 minutes. And for the watermark strategy, we can use for bounded out of orderness. Given that trip data might arrive late due to connectivity issues or delays, and for this case the analysis doesn't need to be real time, so we can use this strategy. So late events can be calculated. Yep, that's all what I want to share with you. Thank you for watching until now. Stay healthy and keep learning. I'll see you around in the next video. Bye bye.